Good morning, everybody. Thank you for joining us today. We are doing the EC Motor and Munters Drive presentation today. My name is Jennifer Midland, and I'm the marketing manager at Munters in the Food Tech division, and I will be moderating today's webinars. A few housekeeping items. Attendee microphones have been muted for the duration of the call. You can submit questions in the question field or communicate with us via the chat function in GoToWebinar. We will be taking questions at the end of the presentation. We have provided a PDF copy of today's PowerPoint in the handouts section. And lastly, a video of the webinar will be shared with you via email afterwards. I'd like to introduce today's speakers, Chris Hause and Ross Demerly. Next slide, please. All right, thank you, Chris. All right, Chris Hause and Ross Demerly are today's presenters. Chris Hause is the R&D manager for Munters, and he's been with the company for 14 years. In a previous role, he was an engineering manager with Fasco DC Motors, where he pioneered the BLDC, Brushless DC motor development program for Fasco DC Motors. He helped develop the Munters Drive and has 25 years of motor development experience. So he is a very technical person, and he will be speaking to the benefits of a lot of different drives, and especially the Munters Drive today. As well as Ross Demerly is on the phone. He is a 30-year veteran of Munters and assists regional sales representatives and customers with product applications and is well versed in value stream mapping, quality management, global application, and research and development. Chris, the floor is yours if you're ready to get started.
Wednesday. Today we're going to cover some motor technology, some of the fundamentals between brushless, BLDC, permanent magnet AC induction motors, and some of the newer switch reluctance technology. So what we're used to, and of course in our industry, is an AC induction motor. Single phase and three phase have been around in the ventilation industry for a very long time. You see them in direct drive as well as belt drive applications. And they generally, you'll see efficiency ranges from 70 to 88%. It's a wide range with AC motors. And a lot of that is you get what you pay for. Higher efficiency motors generally come with a higher price tag, but the payback is generally very quick in terms of usually months. If you buy a premium efficiency product, you will get your money back out of that. They are the most common in the industry. Again, this has been used. It was a standard of the industry and has been up until the last few years to ventilate livestock buildings as well as many other ventilation applications. They're limited to fixed speed ratings at full speed, and it's a function of how many poles the motor has. So as you can see here, general applications are 800, 1000, 75, 1750, and 3500. And you see the associated poles related to each speed point. Switch reluctance. This motor is not new. It was developed a long time ago. 1838 was when it was developed. They can be used in direct drive as well as belt drive applications. They are generally very efficient machines. They can reach 90% and beyond with proper materials as far as system efficiency. And they're generally really good for high speeds, up to and beyond 30,000 RPM. They have to, however, have controls to operate. They will not run without a control, and they have to have sensors to tell the controller where the position of the rotor is. EC motors. I've grouped PMAC and BLDC motors together as they are basically the same. They were poorly named in the beginning when they said a brushless motor as well as a PMAC motor. They are using AC current, changing it to DC, and then managing that DC current to drive the motor. There's two typical designs. There's actually three. I've left one off here because it's not very common and the applications are somewhat limited. Internal rotor design uses a historical NEMA type frame. Looks very similar if you open them up to an AC motor inside. They're quite efficient, right in line with a switch reluctance machine, and the range of 80 to 90% total system efficiency. They also require a frequency drive control with sensorless vector drive capability to run the motor. They can run with trapezoidal drives, but the sensorless vector is generally a much smoother operating low noise method to run the motors. This internal rotor motor design is the most common design. That is a NEMA-based frame. Motor companies designed it to be a drop-in, if possible, with an existing AC induction motor, and that was the intent when they designed that. Another is an external rotor design. Again, direct drive only for this because of the slower speeds. Their system efficiency is much better. They can be upwards of 90 to 94% with basic materials, nothing fancy. They also require a VFD control with a sensorless vector. And they're generally custom designed for each application as their limited operating speed ranges and high torque are really nicely suited for an axial fan, exhaust fan. The motor that I did not mention here, the design didn't mention, is an axial gap machine. And it's more of a flatter pancake, much like the external rotor design, only even shallower in depth. So for some construction details, if you look at an AC induction, I'm sure many of you have seen this design. You have, of course, the rotor here, made up of steel laminations, and it's overmolded with aluminum and turned true and balance with these fins on here to help cool the motor. And you can see again an exploded view here, or excuse me, a cutaway view showing the individual components. Very straightforward. The windings mean a lot to how the motor runs and how efficient it is, as well as how much of the steel stack is in here. The steel and the copper account for the system efficiency and how good that motor particularly runs. Now, for induction machines, they've been the standard in many industries since the early 1900s. They were invented by Nikola Tesla in 1887. They have somewhat low starting torques, so for direct drive applications, it's sometimes hard for them to start a larger propeller or a heavier propeller, so they have had limited applications, especially in the higher power, large propeller applications. Also, the variable speed applications are limited, and you have to be careful when you run the motor speeds down because they are generally an air over motor. You take away that cooling air by slowing the motor down too much and they will overheat. Now they also they do get more efficient at lower speeds, but not anywhere near what an AC machine can do at lower speeds. Now, as you can see here, this is kind of an animation, and what this represents is circles around the outside. This represents the field in the stator of an AC motor. So, and this is running around here for instance, in a 4-pole machine, this is going to be going around at 1800 RPM. Series of circles in the center represents the rotor. Now, if you can see, these are running at a slightly different speed. That's called slip. And if you see over here, the speeds are limited, of course, to the baseline frequency, or 50 hertz if you're in a country that uses 50 hertz. So to figure out the base speed, this 120 is the constant. Time divided by the number of poles equals the base speed. So if we take a 1.5 horsepower 3-phase motor for a typical exhaust fan, and the label will show a rated speed of 1750 RPM, and it's a 4-pole. But if we do the calculation, it's 1800 RPM. Why aren't they equal? And that is from this slip. And what that slip accounts for is that is system efficiency. You are limited in efficiency because you will always have this slip. The rotor's always trying to play catch up to the magnetic field. So the motor is essentially not considered synchronous, meaning that the rotor itself, the motor, the shaft speed never matches the input speed itself to the motor. So what that does, of course, lost efficiency. They can improve slip. You can get it better by, again, adding copper and steel to the motor, increasing the cost, which increases the efficiency as well. A switch reluctance motor. So again, they look very similar. They have a notched rotor. You see these focus the magnetic field. And you can see the rotor is, or excuse me, the stator is wound slightly different. They're generally long single poles, isolated poles instead of overlap, what's called overlap winding with an AC motor. Very similar construction though. Bearings, rotor looks very similar. As you can see, though, quite a bit more steel here present. They tend to be quite a bit heavier for the same power input, but again, see. So switch reluctance motors, I have to be honest, are one of the weaker points in my knowledge of motor industry, motor technology, because it is relatively new. They have been seen increasing use now. Motor controls have evolved, and they were developed way late, but because of the switching capability required, they were never really caught. So it started to be considered as an option, and as the semiconductor industry caught up, and they developed the high power, high speed switching devices to be able to manage them. The motors do require sophisticated drive technology as they're difficult to control under varying load conditions. And they also rely on feedback to manage the motor capability. Their must be precise, the switching schemes. They're known for acoustic issues, vibrations caused by high-speed switching. They'll have a high-pitched whine or a buzz, and as you slow the motors down with a variable speed, they tend to get worse. And what that comes from is you can see the little animation down on the right. That was actual data taken from a switch reluctance motor, vibration data, trying to understand. Obviously, those amplitudes are much larger than what you would normally see. You wouldn't be able to see those, but you could hear them. And you can see above this little animation showing the switching required to run the switch reluctance motor. As they charge each one of these poles, it's pulling a tooth to it. So it is new technology. They're not the controllers are not commercially available. They're basically only constructed for each application for each motor. They are, however, fully synchronous and very efficient machines. You can get above 90% with a switch reluctance motor. Brushless motor, BLDC, and PMAC. Motor construction details. These motors are essentially the same technology. They just look a lot different. These internal rotor designs look just like an AC motor almost, except these will be discrete magnets in here. And then you'll have, instead of being in laminations, and then your coils will be here. Otherwise, the construction looks very similar for an internal rotor design. An external rotor machine, you can see here now, the magnets are on the outside instead of the inside. And they flip the coils. Instead of being on the outside, the stator is now on the inside. So an external rotor, you've also may have heard them called outrunners. They're becoming quite popular. This particular motor here is from a washing machine. If you have a newer model washing machine, chances are this is a motor that's on the back of it if it's a horizontal drum. So Now the Munters Drive construction details you can see is very similar to that. This is an actual Munters Drive, discrete coils here for the stator. And you can see the rotor, the outside rotor is very thin, so it takes up very little space. So EC motors were developed in the 60s, and again, when the solid state electronics started to come on board, they're very efficient machines, easily controlled, can run extremely low speeds, very precise. An internal rotor can be up to just under 90% efficient. An external rotor design, they can be upwards of 95% and more with the right technology and the right materials. And as you can see this little animation here, we have the North Pole and South Pole being blue and red. And as you know, if you've played with magnets before, opposites attract when it comes to magnet, and like poles repulse each other. So brushless motors operate with this push-pull type of method, where you can see this pole is pulling a north charge magnet to it. But as soon as it gets in front, it's turned off. This one begins to pull it, and now this one's pushing it away. So you have very much like a carrot and a stick, where it's always trying to run towards a carrot, but somebody's pushing it with a stick from behind. So they're very efficient. They don't require sensors for operation. There are a number of widely available control solutions to drive competitive pricing for the manufacturers. Many frequency drives in the market will run a brushless motor with the right software and the right programming. These motors are very fully synchronous, and again, you can get precise speed control. Munters Drive, for instance, we can run down as low as 20 RPM and less and still have plus or minus 1 RPM speed control capability. So this animation, again, is what's happening inside the Munters Drive. Obviously, this is just greatly simplified, and I did not cover any of this because it would maybe just be hopefully boring. I hope not. So in summary, the three types that we see and that we see today are AC induction machines. They're the lowest cost. They have many options available: single phase, three phase, a wide range of horsepower capability, and fixed speed capability as well. However, they're the least efficient of all these machines, and they do have limited variable speed capability. They're widely available in the market, many manufacturers, domestic as well as offshore, that you can buy product from. And it is a globally available product. They're available, of course, everywhere. Switch reluctance machines, very high efficiency. They're limited and low speed torque because of their construction. They have electrical noise issues and acoustic issues that I know they have worked on and are improving. But that was one of the chronic issues that limited their applications in the past, is they were very loud. There's very limited options for supply controls to manage these motors. It's not a matter of going to the electronics store and buying a drive. You generally will have to purchase a drive from the manufacturer of the motor. At least, again, this is the best of our knowledge today. There's very limited options for them, and they have an unknown service history. They are new to the market, to our market. They've been out for 2 or 3 years now, but again, not a great deal of installations that we can get feedback on as far as how they're working. EC motors, very high efficiency. Again, multiple variations available, internal and external rotor machines. The supply of drives is wide. You can get drives pretty much from any drive manufacturer that'll make them work with the right software. Broad speed ranges available, anywhere from, for instance, the Munters Drive, the peak operating efficiency speed is about 600 RPM, but there's applications that you can go up to 100,000 RPM, again, with the right construction. They have a very high starting torque based on the construction because they're an external rotor machine, very good speed control, and they can easily manage variations. Like for instance, if side wind loading from gusting winds, or if a building or an overhead door gets opened and the building's under full tunnel or full ventilation, they can handle that no problem and just keep right on going. So with that, I'd like to turn this over to Mr. Demerly, and he'll be covering some of the applications using the Munters Drive motors. Ross, I believe you're in.
Yes. Hello, everyone. We're going to take just a brief minute here as we switch presenters.
You should have it now, Ross.
So bear with us here as we.
Perfect. You look great.
All right. So as Chris explained, the construction of the motor and what the motor is. Now I wanted to get into just a little bit of the uses of the motors themselves. So some field information. We have been using the Munters Drive now for about 8 years in the field. We have it available in a range of product sizes from 36-inch fans to 55-inch fans. And here you'll see in the picture a 48-inch fan on a dark out box in a layer facility. And then on the picture on the right, you'll see Munters Drive in a, I believe this is a swine application. Next, we will get into what is a case study. So the case study we did, one of the first ones we did was a broiler farm in Italy, where they were looking at trying to get better minimum ventilation in their building. So what we did is we took a fan with Munters Drive and we equipped it in here to see what we could do for the building. In the end, here are the results. The power consumption of a belt drive unit doing on-off fans, you can see the kilowatt hours, and then after the flock was done, the kilowatt hours for the Munters Drive was 25% less energy. We also monitored heater usage, and you can see we had a 7% reduction in heater usage, which was mainly due to more even temperature by using the variable speed. Then we took a look at what feed conversion, what we did there, and you can see we dropped from a 179 to a 17, which saved a significant amount of feed over the 55 days, comparing the two houses. Part of the reason, as I said, part of the benefit of that is the variable speed. And as Chris explained, the use of variable speed. One of the things that we want to get into here a little bit is the reasons why the motor is that much better on variable speed. As you can see in this chart here, we have the ventilation curve for the fan, and this is for a VX51 exhaust fan. And if we slow this down, you'll see here, this example takes it to about 50% airflow. We can go lower than that. When we reduce airflow by 50%, the power consumption, though, is going to be cut by about 20%. These motors are made to be slowed down. That's part of the benefit of the brushless DC motor, as Chris was explaining. Now, a couple things here. Can you go lower than 50%? Yes. Can you go down to the 5 RPM or 2 RPM? Yes, you can. The only thing that's going to do is the air moving capacity of the fan at that point becomes not very well. If you're turning at 5, 10 RPM, and especially if you're trying to move air against static pressure in the building or wind effects outside, the ventilation rate that the fan is going to produce is pretty slight at that point. Another case we did where we were comparing some buildings and looking at the effect of Munters Drives was a building set of facilities that we did in Australia. And this chart here, don't get too worried about. It's just our programming sheet here of how we'd set the control up to program. And you can see we were trying to do an A-B comparison, one house with belt drive fans, the next house all with Munters Drives. So what we tried to do is make sure that during the setup of this, we matched the CFM levels in the control so that, airflow wise in each building was pretty consistent. So we were trying to get more of a true A-B comparison between the fans themselves. Well, what does that look like? Well, we took a look at what we would figure the belt drive fans should consume for wattage, what the Munters Drive should consume for wattage at those speeds, and then looked at what savings over the ventilation we should have. And we come up with a calculation of about 31% energy savings. And we did some plots here of what that looks like over the flock of the broilers. Now, this was the actual test result data from the farm itself that they measured. They set up their own monitoring system to try to take a look at the two different scenarios. And as you can see here in the light blue is our building, our shed with Munters Drive, and the gray area is the shed with the belt drive fans. So as you can see over the course of days and over the flock, the energy savings that they were seeing in the ventilation. So sum total of power consumption over the flock yielded a savings of 3,488 kilowatt hours, which amounted to 32% reduction in energy in this flock. So there you can see what some yearly payback savings could look like based on 25 cents per kilowatt hour. Another side-by-side comparison we are working on right now with the University of Georgia is, again, a set of buildings, one set with our WM54 fan belt drive, the other with the WM54 Munters Drive. So here you can see a 36-inch fan, and then here we have our 54s. And over here on the right, we have the same thing. We have a 36-inch belt drive, and we have our belt drive 54-inch fans. So this is a summary for a flock that was run. And as you can see, the fixed speed or the belt drive fans are in the red, And below that, which is good because this is measuring daily power, is the variable speed Munters drives. Up here in the upper left, you can get a summary of kind of what we were looking at. In this particular flock, the reduction in kilowatt hours was about 23%. Now here we had a few things that we're working on and tweaking the control, and we believe that the energy savings, and Mike Zarek does as well, that we should be able to get up in the upper 20s to 30% savings by these tweaks that we're making currently. This is just another way to look at that. It's a breakdown of the daily fan operating cost. You know, and you can see that daily the belt drive fans, which are the same fans, just with a different motor, versus the Munters drive. One of the things we did notice is that the startup of the fan, especially if you're going to run a fan on a timer, the AC motors tend to have a large startup spike, 4 or 5 times starting amp. Some of the motors can even get up to 8-10 times just momentarily as a startup amperage spike. What we see with a Munters drive is a very minimal spike that occurs during this. And so it's easier on the motor. It's also very good for looking at your KWA features when you're looking at sizing generators. When you size a generator, you don't have to necessarily get that much more, be worried about how many fans you're going to turn on at one time. You don't have that large initial rush and startup current to have to worry about. Another case, we were looking at a layer farm, and one of the things we were looking at here is life cycle. And what is life cycle? Heat is a very bad deterrent, very bad thing for a motor and for bearings and so forth. And so one of the nice things about the Munters drive is because it is efficient and it doesn't have the slip that Chris was mentioning, it tends to run significantly cooler than what a belt drive fan would run. And so here you see we're running a house temperature, 28 degrees C, and the motor itself is running somewhere in the 29.6, 30 to 34.7 as the hottest spot, where on a conventional motor, you're running in the area of 50 degrees C, so significantly hotter, which again, that equals loss or efficiency loss in the motor. So as Chris was mentioning, I think he showed you the interior of the Munters drive. One of the things I wanted to point out here is that care was taken when this was developed to design it for our industry. We know the agricultural industry can be very toxic in terms of the gases and ammonia levels and stuff that are produced in the different buildings, as well as a lot of dust, dirt, dander that's in the air. So the bearing itself, as you see in this picture here, the bearing is a totally enclosed sealed bearing, but then it is mounted interior of the motor to where it is then protected from outside environments and pressure washer and things like that as well. Here in the upper left, you'll see, a standard type motor with a bearing with a seal, a gasket, a seal on the outside. That's very good until maybe you hit it with a pressure washer a little too close or one too many times, and then we start having some bearing issues. But again, one of the things I wanted to just reiterate is that the motor itself was designed from the ground up to be used in our environments, and it is good for that. One of the other nice things is that we have seen a electrical savings when it comes to the wiring and the reduction in thermal overloads that are needed to be put in. Now, one of the things that the motor itself does is, if I go back here, the motor can be operated in a number of ways. You can run it on-off. You can run it variable speed, and you run variable speed using a 0 to 10 volt signal. Now, in our case, we've chosen to run that signal as an inverted, where 10 volts is minimum speed and 0 volts is full speed. So in essence, we're running a 10 to 0. Part of the reason we run that 10 to 0 is it's more of a safety. We use that so that if something happens to the control, something happens to the wiring, the motor itself will run then full speed, giving you ventilation as opposed to running in minimum. So again, I know there are some of the other motors on the market that do run 0 to 10. We happen to run 10 to 0, and that was a decision that we made more for safety in the livestock industry itself. In summary here, the Munters Drive is a direct drive EC motor. We do have constant performance through the life of the fan. One thing we didn't really get into a lot is the maintenance issues, belts and pulleys and bearings to grease and wear out. You know, if you have a building like the picture here on the right, that's a lot of fans to grease, a lot of belts and pulleys to wear and maintain. And that's one of the nice things about this this setup with the Munters Drive. It is very robust and reduces your overall maintenance cost. The EC motor does have a higher efficiency than the AC motors, as Chris was explaining. And the natural capability of the fan to run variable speed opens this up for further energy savings in terms of how do you run your ventilation. And we've come up with a number of scenarios to look at for different buildings in terms of what your control is capable of, or if you're putting in a new system, what we can do with the variable speed fans to get maybe more fans on at a lower speed and help run that ventilation. You get the same amount of air, better coverage, and you use less energy by doing that, by turning more fans on and run them at a slower speed. The other thing, based on some of our first studies that we had done that I showed you, the heat savings by doing that in the different climates you're in, as well as further studies to look at what that does to feed efficiency ratios, or egg production output, or milk production, or any of that from the facilities that we put these in. One of the other things is we now have over 30,000 Munters Drive motors in operation to date. So again, we've been selling these motors, putting these motors out now for a number of years, for about 8 years now, and we've had some very good success in the operation of these motors. And with that, Jennifer, I'll turn it back over to you for questions for Chris and I.
All right, let me unmute Chris. Chris, are you back?
I am here.
Awesome, thank you. I just wanted to make sure everyone connected again. Couple questions have come in. What impact does the reduction of the belts and sheaves have on the efficiency?
Ross, do you want to take this, or you want me to take this?
Sure. Go ahead, Chris.
Well, belts and shivs, you know, again, not to bash anybody's product. The last day that the motor or the fan will run at full speed is the day you buy it, unless you maintain your belts and shivs. As the shivs wear, the belt will sink down in a groove and you'll get less air and less air. Now, your efficiency generally will increase because you're not moving as much air and the motor is not working as hard to move air. So it is really important to watch your belts and shivs. And Ross, I believe we recommend once yearly to replace your belts. Is that correct?
That is correct.
Okay. Next question is, what is the impact or what impact does variable speed have on efficiency?
Jennifer,
The
I lost
efficiency.
that. Go ahead, Ross.
The efficiency itself will increase as you slow the fan down. So the air moving capacity will be reduced, and we have ventilation curves. We have variable speed charts for all of our fans, where you can take a look, and we'd be happy to get that information. But as you slow the fan down, it is going to use less energy, but the energy goes down. Reduction goes down quicker than what the drop in ventilation does. So overall efficiency is increased, and we typically see in that 40 to 60% speed range. We're seeing a very good, almost peak efficiency in that range, 50, 60, 65% range itself. So overall, reducing the speed does not hurt the motor at all. Everything is good. The motor is very capable of handling that and being able to be slowed down.
Thanks. Next question is, what is the average lifespan of the motors?
Chris, you want that one?
Yeah, I can. AC induction motors, again, lifespan of those are typically related to the bearing life and when they start to give up their bearings, or if there's an electrical event, meaning a transient coming in on the line or a lightning strike or something from the power company can take a motor out. But they're generally fairly long life. We joke internally that the old motors were much better and that they've taken cost out over the years and shortened the life thereof. But still, with an AC motor today, 5 to 10 years is not unheard of. With an AC motor, if they're running in a good application and they're not, as Ross mentioned, power wash. We don't power wash the seals and the lubricant out of the bearings. For EC motors, they're typically limited to the drive controls. Drive controls, depending on the manufacturer, again, have a life of anywhere from, and I back up just a bit, the life is related to the operating temperature because it's electronics. So they'll tell you that at normal room temperature, you will probably get anywhere from 50 to 100,000 hours of continuous operation, meaning the drive is actively running and driving a motor. And again, that range is huge depending on the operating temperature. Munters drives, we usually run very, very close to room temperature. So we've gotten very good life out of the drives. And at this point, nothing in the field has reached its life capacity. The drives do have an indicator inside that the service team can predict the life of the drive just by a simple reading. Again, switch reluctance motors, unknown. I don't have a service history, and I don't think they have a long service history either in this application. A little rather wordy answer, but
I hope that helped. Next question. Do you have any case studies on how much you could save or how many years an average payback would be with electric usage for a Munters Drive versus an AC motor?
Yes, the studies that we're doing and that we've looked at are in the range, depending on how you use it and what market you're in, how many hours of operation you would be using these, really comes into play. And we'd be happy to do, you know, a custom ROI for anyone. But generally, we're looking at about 30 to 50 months. You know, so 2.5 to 4 years on a payback, depending on how you operate the fan. If it's your last stage you come on, or if you allow the fans to come on sooner and run more. A broiler type building versus a dairy building will have a lot more runtime hours on the ventilation side. So there's a lot of factors that go into predicting that, but yeah, somewhere in the 2.5 to 4 year payback.
Okay. Next question that came in is, what is the cost of an efficient EC motor?
Jennifer, I missed the last piece. There's a couple
Sorry,
words.
what is the cost of an EC motor?
Well, an EC motor, that's variable by a huge margin. If you do a relative comparison, for instance, if we just pick a single motor, okay, a single performance point, like for instance, a 1.5, 2 horsepower NEMA 56 frame motor that's common in our industry. Generally, an EC motor is going to be 3 to 4x that cost if you include the variable speed drive. And keep that in mind. Motor is just basically on and off. Have to consider a variable speed to make it as you would say, apples to apples. Again, the motors are sensitive to features, what you get, what you want. You know, there is just such a huge range in EC motors and the cost of them.
Do we have any more questions that have come in? I don't see any more that have come in. I'll give maybe another minute or so for last questions to be submitted. If you're thinking of something and you want to ask, now is the time. Otherwise, we will wrap this up in about a minute. If there's anything
to expand on Chris's there a little bit, typical what we've seen in the industries, you're typically in anywhere from a 2 to a 4x multiplier over a standard AC type motor, depending on, as Chris mentioned, all the features and setup of and type of motor that it is.
I don't see any other questions. If you have specific service questions, you can get in touch with us via email or via phone. And those phone numbers are on the website. And again, just a reminder that we are sending out an archived version of this PowerPoint an archived video of the webinar today. And you will have that in your email from us after the presentation. So I wanted to thank everyone for joining us for today's session, especially Ross and Chris for sharing your knowledge. Really appreciate it. And we hope to see you guys soon. Thank you.
Thanks, everybody.
Thanks, everyone.